Hello friends, myself Dr. Parashram Pal, Professor in ABES Engineering College, Ghaziabad. In the previous lecture, I have discussed about the cache memory and various kind of mapping of the cache memory. In this example, I am going to solve some examples based on the cache memory. This is the first example. Let's read first this example. The access time of the cache memory is 100 nanosecond and that of main memory 1000 nanosecond. It is estimated that 80% of memory requests are for read and remaining 20% for write operation. The hit ratio for read access only is 0.9. Write-through procedure is used. Now the first question is, what is the average access time of the system considering only memory read cycle? So here, let's first analyze the problem. Here, the cache memory access time is 100 nanosecond and that of main memory access time is of 1000 nanosecond. That means when we perform or when CPU generates an address for memory, it will be searched first in the cache memory. If hits, the data will be fetched from the cache memory and it will require the total time, that is the 100 nanosecond. In case data is not found in the cache memory, then it will have a miss and then the data will be fetched from the main memory. So what will happen? The access from cache memory will take this 100 nanosecond, but if miss occurs, in that case the access will be from the main memory. The access from main memory will take this 100 nanosecond of the miss operation on the cache as well as the 1000 nanosecond of the access time of main memory. So the hit operation will take 100 nanosecond and miss will take 100 nanosecond to identify that there is a miss and 1000 nanosecond to access the data from main memory. That is the nanosecond. That will be 1100 nanosecond for the miss. Now the hit ratio for read access only is 0.9. That is the hit ratio is 90%. So out of 100, 90 requests will be hit. So 90% access will work for this one. That can be also said by 0.9. And the remaining 10% will be miss operation. So for the remaining 10% request will be fulfilled from the main memory due to miss, or we can say this as a 0.1. Okay. So the first question is saying, what is the average access time of the system considering only memory read cycle? If there are only memory read cycle, then 100% requests generated by the CPU will be only for the read purpose and they will apply here. Okay. So the answer of this is given in this solution part. So 90% this for the hit purpose, 90% are hit, so 0.9 is for that, and for each hit there will be 100 nanosecond from the cache access. Okay, the remaining for miss point of view, this part will work. The remaining 10% or 0.1 are the miss operation, and for that purpose we will access the data from the main memory, and main memory access is cache access to identify that there is a miss, 100 nanosecond and 1000 nanosecond for memory access from main memory. So it will become the 1100. This is misprinted. This is exactly 1100, not 11,000. Okay. So we'll calculate. This will become 90 and it will become the 110. If we add both, it will become the 200 nanosecond. So the average access time for this problem will be 200 nanosecond. The next question is, what is the average access time for the system for both read and write request? Now we are considering both the read and write request. Now in this case, since we are considering the write as well as the read request, and as in the problem they have said that the 20% are for write and 80% are memory request are for read. Okay, so 80% means either you say 80% are for read, or we can simply write 0.8 out of 1. Similarly, write request are 20%, or simply we can write 0.1 out of 1. Sorry, 0.2, not 1. Okay. So whenever there is a read, whenever there is a read, this will work on this 0.8. So 0.8 and average memory access that we have calculated here in the A part, that is the 200. Sorry, this one 0.8 and 200. So this is for the 80% of read. This is for the read purpose. Remaining 20%, that is 0.2 for the write. And for the writing, what is the memory access time? That is shown here, that a write-through procedure is used. Whenever CPU writes into the memory, there are two techniques. One is, I am writing here, one is write back and another one is write through. In write back, what happens? The CPU writes into the cache, that is, the CPU is connected to the cache memory and CPU is connected to the main memory also. Okay, and cache memory, main memory in this way. See here, see this diagram and this one. In the write back, the CPU writes only in the cache memory, and whenever that block has to be evacuated from this cache memory, then it is written into the cache main memory. This is the write back process. But in write through process, what happens? The CPU writes in the cache block as well as simultaneously the main memory block also. So this writing in CPU to main cache memory, it will take 100 nanosecond, but writing simultaneously to the main memory, it takes the 100 nanosecond. Sorry, 1000 nanosecond. Okay, so whenever data is written using the write through process, the longest time duration taken to write the data into the main memory will be considered. So that's why it is taken here for the write purpose. So 20% request will take the 1000 nanosecond. So we have multiplied by this one. So this will form the 200, and multiplication 0.8 into 200 will form the 160. If we add both, there is the 360, which is the average access time considering the write cycle also. The third question is, what is the hit ratio taking into consideration the write cycle also? The hit ratio when we are taking the read only, it's 90% of course, and when we are considering the write cycles also, write request also, then out of 100, only 80% are read, and since hit ratio is for only read purpose, so the hit ratio for this is considered. For those 80%, the 0.9 hit ratio is multiplied, so the hit ratio will be now 0.72. So this is the answer of this problem. Now we are moving to the next problem. In this next problem, we have a digital computer has a memory unit of 64K by 16 watts. This is the size of the main memory, and a cache memory of 1K word. This is the size of cache memory. Now the cache use direct mapping. We are using here the direct mapping with a block size of 4. Block size is 4. So this is important. 4 words. Okay, now what's the problem? How many bits are there in tag, index, block and word fields of the address formats? So we have to find out this one. So let's we see here that we have the main memory size of 64K words. So out of these 64K words, how many number of bits we need to address the main memory? It can be calculated something like that 2 to power k equal to 64k. It can be written like 2 to power 64 can be written like 2 to the power 6 into k is written like 2 to power 10. It will form 2 to power 16. It will give us k equal to 16 bits. So k with 16 bits address is required to address the main memory. Similarly, in this case, we will calculate the number of bits required to address the cache memory. So there are 1K words. So we can write here like k equal to 1K. This k is different than this k. And this k is a variable and this k is for kilo. It can be written like 2 to power 10 as 1k is 2 to power 10. It shows the value of k, this will be 2 to power k equal to 1k. So k equal to 10. So 10 bit address is required to address the cache memory. As we have earlier told you that the index field always contains the size of this k. So what is the size of k? That is the 10 bits. So this will have the 10 bits. Size of the index will be 10 bits. Now total address of 16 bits. So we have earlier told you that n minus k is the tag size. N is here what? This 16 bits. And k is what? 10 bits. So 16 minus 10, that is the 6 bit. This is the size of the tag. Okay. So we have find out the size of tag and size of the index. Now further, since the data transfer between the main memory and cache memory is in terms of the block, and here they have provided the size of block is 4 words. That is, there are 4 words in a block. To address these 4 words, we need 2 bits. We need 2 bits to address the word. To address the word, we need 2 bits. And this index part is further divided into block and word. This part is further divided into 2 parts, that is the word and block. The word field is having the 2 bits, so the size of word field will be 2. Remaining 10 minus 2, that is the 8 bit will be size of the block. The same is shown here. You see here in this A part, tag is having the 6 bit, block is having the 8 bit, word is having the 2 bit and index is having the 10 bits. Now the second question is saying how many bits are there in each word of the cache and how are they divided into functions. Include a valid bit also. This is a okay. Now see here, how many bits are there in each word of the cache? In the cache, whenever data is transferred from main memory to the cache memory, the data size in the main memory, along with its tag is stored over there. In this case, they have included the valid bit also. So valid bit also we need to add in this one. So include a valid bit. The size of valid bit is 1 bit. The tag here we have find out, that is the 6 bit, and the data size, that is the word size of main memory in this case is the 16 bit. So 16. If we add all these bits, it will become the 17 bits. Okay. So how many bits are there in each word of cache, and how are they divided into the function? So this is the function, how they are divided. It is shown here that one bit, valid bit, tag is having the 6 bit and data is having the 16, yes, of course 16 bit. So this will be 23, I am seeing here. This is the 16 bit, 16, 6, 22, that this will become 23 bits. Now the next question is, how many blocks can cache accommodate? How many blocks can cache accommodate? In the block field, we are having the 8 bit to address a block. So the number of blocks can be given by 2 to power 8. So it will be 256 blocks, and each block will have how many words? 4 words. Okay, so this is the answer of C part, that is 256 blocks of 4 words each. So this problem is over now. Now we are coming to next problem. Here is the third problem, and let's go through that. A two-way set associative memory. Very important word is two-way set associative memory. Two-way. That is, what is the meaning of this one? That at one index there are 2 words stored. If we draw it here, suppose this is the diagram of cache memory. Okay. So at this index there will be 2 words. Word 1, word 2. Similarly for all words. So this is the meaning of 2 words. At this index there will be 2. There will be tag of this and data of this. Similarly here, tag of this and data of this. So we have always to keep it in mind. Okay. Now, set associative cache memory uses blocks of 4 words. That is, there are 4 words in a block. So it immediately tells us the 2 bits are needed to address a block. 2 bits, since there are 4 words in a block, so 2 bits are needed to address word. 2 bit address. Okay. The cache can accommodate a total of 204 word from main memory. Cache can accommodate 2048 word from main memory. That means is at one index location there are 2 words stored and 2048 word from the cache. So if we divide 2048, then we will find the number of words of cache. These words are not up for cache. These words are from the main memory. So if we divide this 2048 divided by 2, that is 1024. Number of words will be in the cache. 1024 words in cache and 2048 words of main memory, because each index location is having 2 words of main memory. So this 1024 for this purpose will require 10 bit of address. 10 bit of address to access the cache. 10 bit of address to access the cache. That means here from 0, 0, 0, 0, that is from 0 to, I am writing in decimal number 1023. These will be the indices. Okay. And at each index there will be 2 words of the main memory. Now the main memory size is 128 by 32. So what will the address of the main memory? Since there are in main memory there are 128 keywords. So we can find out 2 to power k equal to 128k. It will give us 2 to power 7 is 128 and k means 2 to power 10. This means 2 to power it is 17. 2 to power k is equal to 17, that is k equal to what? 17. So 17 bits address size will be for the main memory. Now what they are asking, formulate all pertinent information required to construct the cache memory. What is the meaning of pertinent? That is the all important information. What are the various important information? That what will be the size of the memory address, how it will be divided into the tag, index, block and words. So we have to find out all these here. In this case, the total size of address is 17 bit. Since there are 1024 indexes in the cache memory, therefore 10 bit will be size of an index. So it will be divided such as tag, index. So index will be what? 10 bit. Remaining 7 bits will be of tag. Now further, this index is divided into block and words. Since there are 4 words in a block, so we need 2 bits to address a word. The size of word will be 2 bit. Out of these 10, 2 bits will be used to address the word, and remaining 8 bit, that is 10 minus 2 is equal to, that will be size of block. So all these things are shown here. The A part, 7 bit tag, I told you, 10 bit index, and block 8 bit, and words 2 bits. Now the next part is what is the size of cache memory. Now see here, in cache memory, tag, size of cache memory can be, how we can find out? The tag plus data bits, and we can multiply it by 2 because there are 2 words there. So we can find out here 2 inside the bracket. Tag is of what size? 7 bit. So 7 plus the index is, sorry, not index, the data. Data size is what? 32 bit. Here 32 bit data in main memory. Okay, so 32. Now it will become what? It will be 39, that is the 78. So each word of cache will be of 78 bits. And how many words of such kind in the cache? They are 1024. The size of the cache can be written like 1024 into 78. This is the size of the cache, which is shown here. The size of the cache is given by 1024 by 78. Okay. So this is the third example with its solution. Thank you for watching my video.